thank Dr. Weglein for introduction. And this is my talk. My talk has a very long title. But basically speaking, I'm talking about the amplitude information, or to be specific, angle-dependent amplitude information about wave equation migration and asymptotic migration. So first, we start from some background, and most migration methods involving wave equation usually have two integrants. One is the wave propagation, one is some image principle or concept or image condition. As Dr. Weglein has introduced in the last talk, there are three key image conditions. The time-space coincidence of upgoing and downgoing wave, which is used by the RTM, conventional RTM, and the exploding reflector model, and predict a subsurface impairment with zero subsurface offset, or the coincidence source and receiver, and then ask for time equals 0. For the normal instance, normal instance plane wave or the 1D case, all of those three image conditions are totally equivalent. But for the case more than 1D, more than normal instance 1D, or we have the offset with 1D, or we have 2D or 3D case, those three are not equal. It's not equal. And for determining quantitative information, obviously we'd better use the third one, because we have some impairment that has physical meaning of that image condition. We have predicted a subsurface impairment. And then let's look at the wave equation migration. The wave equation migration, or sometimes I use the short term WEM, is defined as that using the third image condition. And all other two image conditions, the first and the second one, in the 1D with offset or 2D or 3D case, in fact, a kind of asymptotic approximation or Kirchhoff approximation of the third image condition. Dr. Weglein has mentioned already there are three key advantages or benefits of the third image condition. First, we have definiteness of the subsurface point corresponding to a structure or not. If you use asymptotic migration, usually you have some candidates, like you have ellipse for the Kirchhoff migration, and then you do the constructive summation. The coherent part of the candidate will be enhanced, and then you get the structure map of the image. But for the wave equation migration, the image condition 3, you can tell that whether a point belongs to a structure or not. Second is the main point of this talk is you have quantitative angle-dependent reflection coefficient or angle-dependent amplitude information from the wave equation migration or from the third image condition. I will talk more later. And the third one is that you have well-spread wave propagation, because you know that a wave just go anywhere, but the ray just go along the ray's path. So by using wave equation migration, you have less illumination problem compared to the ray-based theory or ray-based algorithm, like Kirchhoff migration or asymptotic migration. So the second advantage will be the major part. We will focus on the second advantage of this in this talk. We will do some comparison based on some tests on the amplitude, angle-dependent amplitude of wave equation migration and asymptotic migration. Before we can do that, we need some implementation of both of the methods. So before I show the result, I will introduce what we did for the two different methods. First, let's look at the implementation for the wave equation migration. The idea of wave equation migration we have already talked about has 3 steps. First, we have the data at the surface, measurement surface, and this is the source location, receiver location. We have both steps equal 0 in that surface, and we have the time. All the data is the function of time. Then the third step, first step is that we bring the source down to the depth subsurface. And here I just draw 1 point, but in fact we need to bring the source down anyway. In this, if we have a complicated medium, this will not be an easy task, not a piece of cake, like Professor Weglein has already mentioned. If you have two-way wave propagation, you need some Gaussian wave prediction with boundary conditions, special Gaussian function to do that. And after the first step, we have the source at depth, but the receiver still at surface. Then we go to the second step, we bring the receiver down. So now we have the both source and the receiver at depth. And then we go to the third step, just we try to apply the image condition. Before that, the first thing we do is change the coordinates. Before we change the coordinates, we have the source and the receiver coordinates. After that, we use the middle point and the offset. And please notice that this middle point and offset is a subsurface middle point and a subsurface offset. It's not the middle point of the offset at surface of the acquisition. Then we apply the image condition. The image condition is that, that we have the source and the receiver coincidence. In another word, is that the subsurface offset equals 0. We put both source and receiver together with it, and we ask for time equals 0. We have the image. The image is the function of depth and the location, the horizontal location of the middle point, or the image point. So we have idea what's the step one by one, and we want to implement of this wave equation migration. Because our point is not just to compare different migration wave equation migration scheme. Our point is to research the angle-dependent amplitude of wave equation migration and asymptotic migration. So we want to use the simplest possible implementation for both scheme, wave equation migration and asymptotic migration. What's the simplest possible scheme, situation for wave equation migration? The answer probably is that we have a medium consists of two homogeneous half space, and we have the source and the receiver in the upper half space, and here, and the depth equals 0. And we have a lower half space with different velocity, and keep the model acoustic. We do not have the density. That one will be the simplest possible situation for implementing wave equation migration. In this case, the reference medium is simple. It's just a whole space homogeneous with the constant velocity. Why we choose that? Because this is the acoustic wave equation in the reference medium. It's constant medium, so it's very simple. After we choose this situation, the reference in the reference medium and below the measurement, below the receiver wave field propagation is one way, only upgoing. There is no downgoing receiver wave field. And given the one-way propagation and the homogeneous reference medium, the first step and second step is very easy. We do not need the Green theorem prediction, or we can do that easy. First, we want to put the source down, downward continuation to the source, put the source down, because we have the homogeneous medium and the one-way wave. We can use that phase shift to do that. Very easy. It's only a phase shift. And then from the reciprocity, we can use the phase shift to the second step. This one we just put the source from the zero depth to the depth, subsurface depth, and this one we just put the receiver also at depth. Then we apply the image condition, and here just we put the location of the source and the receiver to be equal. both xg equals x and xs equals s and then x, sorry, and ask for time equals 0. Here we have the integral over omega. That is equal to ask times the time equals 0. And here we just set the both gx and sx equals to x by doing this exponential thing. Then, like I described in the 3 steps, we need to change the integral variable from the sx, gx, omega, from the source location, receiver location, frequency, to the middle point, offset, and depth. We use that as a simple relation between them to do the changing of variable. And in fact, we have Jacobian here. You can find the detail in our report. But here we just skip that mathematical step, and we get this formula, this expression. If we look at this formula, we will find this integral here and this integral here over z and x, plus those two equivalent factors are in fact two inverse Fourier transform. We do not need that, so we just remove those two inverse Fourier transform. We get the very simple, or simplest one-way wave equation migration formula in wave number domain. It's here. But look at that. In this result, for the image at some image point, there is only one number corresponding to that. So for one image point, we have only one value or one number or scalar corresponding to the point. We are looking at the angle-dependent amplitude information. In this image, we do not have the angle-dependent amplitude information. We need more freedom to get that. So let's look at this integral over kh. What's that? That is introduced by the image condition. Because we said that the big image condition is that we have the source receiver coincidence equals to the offset, subsurface offset equals 0. That means that we just sum or integral over the subsurface offset wave number to get the subsurface offset equals 0. If we do not do this integral, like we look at the integrand of this integral, in this, we are looking for something like angle-dependent information. In this image result, we have only one, like I said, we have only one value for each image point. That value is kind of average of all angle. So we need something before we do this image condition. Or we just relieve that image condition. We not only ask subsurface offset equals 0, we keep that subsurface offset freedom. Like in this, we have this integrand here. By doing this, we have in this integrand, we have not only the location, the depth, and the horizontal location. We have also one freedom of subsurface offset. By keeping this freedom, we can keep the angle-dependent information in that one, in that image. Okay, I forgot to mention. This one is also called unclasped migration image, because we do not do this summation over the cage. It's unclasped. So we have the implementation for the wave equation migration. Now we want to do the same. We want to have the implementation for the asymptotic migration. We want the comparison to be fair, so we started from the one-way wave equation migration scheme we get in previous slides, and we want to add some approximation, asymptotic approximation into that to get asymptotic version of the migration. Here we started from this also called Stolt migration formula, just in I think 2 or 3 slides before. And then we bring the data from the wave number domain, wave number frequency domain to the space-time domain by doing some Fourier transform, or inverse Fourier transform. We got this one. And then we try to introduce the stationary phase approximation. These are the two. This is the stationary phase approximation. What is that? We look at this left-hand side. If we want to do some integral on some function, like on some exponential function like this, and this is the oscillation function or oscillating function. If we want to do the integral for the graphical oscillation part, the positive and the negative part, the positive value and the negative value should be cancelled each other. So only the slow variation part, slow oscillating part is important or significant for us to evaluate this integral. So we can just, instead of do the whole integral, we can evaluate this whole integral by evaluating some function, some formula on the stationary phase point, or the stationary phase point, the slow change part. And then here, the RS and RG is just the distance between the source location and the image point, and between the receiver location and the image point. By introduce those two stationary phase approximation, we have this asymptotic version migration. This is the one-way asymptotic migration here. And we did the same thing. We just do the change of variable from the source and the receiver to the middle point and the offset. We get this formula for the asymptotic migration, one-way asymptotic migration. And I want to emphasize one point here. After we do the approximation, after we do the asymptotic approximation or the stationary phase approximation, we do not have any requirement, subsurface requirement corresponding to this imaging. This is just the asymptotic migration. This is not the source down, receiver down, and ask for source receiver coincidence. So this middle point and offset is not the subsurface middle point and offset. That is the middle point and offset at surface. Is the middle point and offset in the data, is in the acquisition. And then this, I put a tilde on the x-edge and x-edge to just distinguish that from the subsurface middle point and the offset. If we look at this formula, it's kind of familiar, right? We look at the data. This data is, in fact, is the data over some trajectory or short-time curve. T equals R over C. R is the read path from the source to image point and image point to receiver. So if we compare this result to the general grid theory-based Kirchhoff migration formula like this, we have the similar data. It's the data over a 12-time curve, and we have some weight function and summation. We have integral of the weight function combined with the data over 12-time curve. We have the Kirchhoff migration result. We compare those two formulas. We see the data are same, exactly the same, and we have the exact integral variable. If we think about this other part, this one, this one, this one, it's kind of weight function W here. These two are in fact the same. So we say that this asymptotic migration scheme we get here, we got here, is the prototype of Kirchhoff migration. As I have mentioned, we get the asymptotic migration in this case. However, this image is not corresponding to any subsurface experiment. So we cannot get the subsurface offset information, and that will cause a problem. How we get angle-dependent amplitude information from that. We have only one value for one image point, the same problem as we have in the wave equation migration. But this time we cannot solve that by just relieve the image condition, remove the substrate of equal 0. How can we get angle-dependent information in this scheme? This is the next step we want to show angle-dependent information from this asymptotic migration. Like I have said, this asymptotic migration result does not come from the coincident source receiver experiment at depth. But we want to know we want to obtain our angle-dependent amplitude information from that. So how can we do that? We have two different ways to do that. We have two ways. And the first is that we interpret that this is the correspond to a subsurface experiment with coincident source and receiver. We just imagine that this is the subsurface offset, subsurface experiment with subsurface offset to 0, which is not. But we just imagine it, we just interpret this as this. So we treat this asymptotic migration with the image as the summing experiment at the middle point depth, middle point offset depth with the subsurface offset equal 0. This is the only assumption. That the assumption is some assistant we introduced to the asymptotic migration just for helping to get angle-dependent information from the asymptotic migration scheme. By doing that, it's not enough because if we want to have the freedom of the subsurface offset, we need to answer what's the value of this image with the non-zero subsurface offset. From the causality, we assume that for all subsurface offset not equal to 0, the image, the value of this asymptotic migration result is 0. Because if you put some source receiver at some depth with some distance and you ask for time equal 0, the answer probably be 0 because the wave needs some time to travel from the source to the receiver. Now we have this. We have also subsurface offset information or subsurface offset freedom for the asymptotic migration. So we can compare the wave equation migration with this asymptotic migration in terms of angle-dependent amplitude information. As I said, we have two ways to try to get the angle-dependent information from the asymptotic migration scheme. The alternative way, the second way is that constant offset partial asymptotic migration. What does that mean? We back to the wave equation migration case. And in wave equation migration, we look at some integrand. And then before we do the integral over kh, this integrand has the kh information or kh freedom. So we can have the subsurface offset information in the wave equation migration. If we look at the formula for asymptotic migration, we also have integral over kh, xh here. It's not kh, but it looks like a kind of similar. Can we just look at the integrand of this integral and get the xh information to treat that as we have subsurface offset? One thing I want to emphasize, we have already know that this xh, we have a tilde. This is not subsurface offset. This is the offset on the surface. Surface offset is in part of the geometry of the acquisition. So this, by doing this integral, it's not a kind of the image condition like this. It's just to saying that we need to use all data of different offset to get the image. For the integrand, for a fixed xh here, it's just the result of one consistent offset or single offset for the asymptotic migration result. And we do this integral, combine all surface offset data to get the whole image. This is not as we did here. Here, for one case, only for one case, we have the image result for all data. We do not need only part of data. So we call that uncollapsed migration. But here, if we do not do this integral, for a fixed xh field, we only use part of data to do this asymptotic migration. So that is not an uncollapsed migration, but a partial asymptotic migration. Partial means that we only use part of data to do that. So this one is not equal to this one. However, we can just pretend this one is similar as the previous I showed. We pretend this subsurface offset to be this surface offset to be subsurface offset. Like we pretend this term is this term, and you try to use this formula, this migration scheme to get an angle-dependent reflection coefficient. I will show that this idea will not work. We cannot get angle-dependent amplitude information from this scheme. The second, the alternative of the second. Now, from the beginning, I talked about test and comparison of the angle-dependent amplitude of wave equation migration and asymptotic migration. Now we can show the result to you, finally. So we will demonstrate the difference between the wave equation migration and asymptotic migration in terms of angle-dependent amplitude information. Here is the overview of our scheme. We have already introduced how we implemented the wave equation migration and asymptotic migration. Next, we will show you the model data we use to generate the data, and we will show the result and to do the comparison. The model we use is, like I said, is a two half-space homogeneous model, and we put the depth of the interface on the depth of 200 meters. I use the upper half-space velocity equal to 2,000, and the lower half-space velocity equal to 1,500. We put the higher velocity over lower velocity just because we want to avoid the post-critical angle part in our forward modeling scheme. Then I will show the data we use for the test. We use the analytical data for both wave equation migration and asymptotic migration. The reason we use the analytical data rather than some for the modeling, like a finite difference for the modeling or some numerical for the modeling result, because we want to effect any numerical inaccuracy in the data generating procedure. Like we want to attribute the O difference in the result to the scheme, to the equation, to the migration, to the difference between the migration scheme itself, not the data. So here is the data we used for the wave equation migration. First, we look at the migration, the formula for the wave equation migration we will use. So this formula is asking the data in wave number and frequency domain. So we need some analytical data in wave number and frequency domain. Here we use the reflectivity method to generate this data. This method is widely used method. For example, it can be found in the EGP book 1957, and here is the formula we use. This R here is the angle-dependent reflection coefficient. We have the formula for that from the analytical form. Now let's look at the data for asymptotic migration. From the formula, we know that the asymptotic migration is asking data in space-time domain. And we use the Cadenia-de-Hoof method to generate analytical data in space-time domain. Here is the formula for this Cadenia-de-Hoof for the data generating scheme. This is also widely used method. And for example, this same formula is used in Qiang Fu and Weglein 2005 M-OSRP report. Now I will show you the result we will show the comparison of the result for the two different migration methods. Before we do that, we still have a small problem to solve. We have already know that the asymptotic migration result is in the space domain, and the wave equation migration result is in wave number domain. We cannot compare those two results directly, or it will be apple to orange comparison. We want to bring them into the same domain to do the apple to apple comparison. So we just use a bunch of Fourier transform and inverse Fourier transform to bring the result into different domains. Let's look at first we look at the different result in the space domain. It's the depth and the subsurface offset domain. Here is the result. We say that for both image results, we have only non-zero value at the subsurface offset equals 0. For the asymptotic case, this is by assumption. We made that this. We made the assumption like we have only non-zero value for subsurface offset equal to 0. For the wave equation method result, it comes from the causality. Like I said, you put the source and the receiver down, you do the physical experiment. If the subsurface is not zero, it's not equal to 0, you ask for time equal to 0, probably the result is 0. I just put two arrows here so you can see that the depth of the event clearly, but still it's kind of hard to see because we have only one trace, non-zero here. So we do a Fourier transform along the horizontal axis, bring the result to the z depth and the wave number domain. This kh is the wave number of the subsurface offset. From that, we can see for both image results, the location are correct. It's at the 200 meters. This is where we put the interface exactly in the model. So the depth information has no problem for the both migration method, asymptotic and wave equation. Then we just do a further Fourier transform, bring the result into the wave number domain. Here is the result in wave number domain. The vertical axis is the kz. That's vertical wave number, and this is the kh, wave number of the subsurface offset. And we want to get the angle-dependent amplitude information. So we figure out a formula which can calculate the angle-dependent reflection coefficient from the wave equation migration result. This is the formula. And we just skip the detail of the mathematical derivation. If you want, you can look at the report. There has the full derivation for that. One problem is that we know for the angle-dependent reflection coefficient, there should be a real number. It's not a complex number. And here we have some phase factor. In ideal case, that should cancel the phase factor in the image in the wave number domain. But because some numerical issue in the real case, this cannot be exactly cancelled. So we will get some number, complex number with a very small imaginary part. That is not easy to show the imaginary number. So we decided we not show the number itself. We show the amplitude or the length of the complex number. We just put a norm here. We get a norm for this inverse angle-dependent reflection coefficient. Before we show the inversion result, we show the analytical result. This is the analytical reflection coefficient in for our model. This is calculated from this formula. This vertical axis is the vertical wave number, and the horizontal axis is the horizontal wave number. We can see that one feature is that for all straight line passing the origin, the reflection coefficient is constant. That's because for all straight line passing the origin, the ratio of the vertical wave number and the horizontal wave number is constant, which means you have a constant of angle. the angle-dependent reflection coefficient should be a constant along the constant angle, right? So we have that feature. And this is the feature we want to get from the migration result. This is the result from the wave equation migration. The angle-dependent reflection coefficient we get from the wave equation migration. If we go back and forth, we can see that except the very small vertical wave number part, the results are almost identical. Oh, sorry. For the difference in this area, you probably remember in the scheme we have a division of the vertical wave number. So for the small wave number part, small vertical wave number part, we have some instability issue by dividing a small number. That is why we did not get a perfect result in here. But besides that, others are just perfect. Oh, almost perfect. Here is the reflection coefficient, angle-dependent reflection coefficient result from the asymptotic migration. As I said, we have two ways to get angle-dependent reflection, angle-dependent information from the asymptotic migration. And first is that we pretend that the result is corresponding to zero offset experiment. Second is that the partial asymptotic migration scheme. This is the result. This is the result of the first method, the first way. If we look at this result, it has some similar feature here. We have the lower value here, larger value here, but we miss the most important feature that we have this constant reflection coefficient for constant angle. We do not have that in this result. So that means that asymptotic migration scheme method, even they provide further assistance, provide further help, further information or assumption to help that to get angle-dependent amplitude information, we can still not get that. As I said, we have another way that just use the partial asymptotic migration to try to get angle-dependent amplitude information from the for the asymptotic migration. By doing this, we just try to pretend this surface offset as the subsurface offset, and use this formula to replace this term, and try to use the same formula to get the angle-dependent reflection coefficient. This is the result. Those parts are all zero. Only one small region near here is non-zero. So this scheme is totally failed. In fact, this idea is not new. It's a very common practice this is a common practice in the world, as we just use avoid to do the integral over the xh, and use that as the subsurface offset information of the asymptotic migration. But this example told us that this is not. This is the only surface offset. This one cannot provide the subsurface offset information or angle-dependent information. Now let's draw the conclusion. So we compare the angle-dependent amplitude of the wave equation migration and the asymptotic migration for the simplest possible overburden, using both perfect data in the domain each method requires, and seek to retrieve the angle-dependent reflection coefficient from both migration methods. The amplitude of wave equation migration is closely related to the angle-dependent reflection coefficient of the reflector in the wave equation migration method. So we can retrieve the angle-dependent reflection coefficient from the image. And the amplitude of the asymptotic migration is not really related to the angle-dependent reflection coefficient. So in this game, we cannot retrieve the angle-dependent reflection coefficient, or correct angle-dependent reflection coefficient from the asymptotic migration scheme or method. And attempt to interpret the asymptotic migration result as a subsurface experiment corresponding to source receiver coincidence does not provide the angle-dependent reflection coefficient or angle-dependent amplitude information. This conclusion is for the first way we try to give some help to asymptotic migration. And the common practice in asymptotic migration of calling constant offset partial image or partial migration in attempt to deduce angle-dependent information at the depth at the output point is showing that is not corresponding to the angle-dependent reflection coefficient at the output point. That is the second way we want to try to help the asymptotic migration to get the angle-dependent reflection. Both are not work. And we want to thank all SMIC sponsors for your help and support, and thank you all for attending.